Hello and welcome. My name is Mike Nichols and I'm the Content and Social Media Manager here at AEM. And on behalf of our entire team, I want to thank you for joining us today. We're really excited about today's session on forecasting flood threats. First up, we've got James Logan. James leads the AEM water sector. He's been involved in the assessment, design, development, implementation of more than 200 automated early warning and environmental monitoring systems across the US and abroad. He's also led numerous consulting studies related to rainfall and hydrologic analysis, flooding, stormwater, dam safety, hydrology, and water resource management. James is also a member and contributor to the US National Hydrologic Warning Council's technical working group for the Alert 2 protocol standard. Then we've got Chad Ballard. Chad is a licensed civil engineer in multiple states and a certified floodplain manager. He spent his career working with clients to solve challenging water resource problems using the latest advances in hydrologic and hydraulic modeling. He's taught undergraduate, graduate, and professional continuing education courses in water resources and is active in a variety of professional organizations, including the American Society of Civil Engineers and the Environmental and Water Resource Institute. So with that, I will go ahead and turn things over to our first speaker, James Logan. James?
Thank you, Mike, and welcome everybody. So I'm going to go over the overall framework we have for dealing with multi-hazard early warning systems. So the structure that we have, it deals with first understanding the risk and where the risk is, the biggest areas of risk that you have, and risk is a cross between where the hazards will happen and where the people that are vulnerable to those hazards exist in the same places. And so that information is really important for both the designing and building of the system, and it's important for understanding risk as a particular event is happening. And then we'll talk about monitoring and forecasting for that type of hazard that we're dealing with. And then the next step is how to communicate that information to either public safety agencies or to the public. That's part of the system. And then finally, the response, which is really the emergency action plans that get executed during the hazard so that people know what to do during an emergency, and all the people involved have some structure to the way they deal with moving themselves out of harm's way or whatever the situation is. And then finally, every time there is an event, we do evaluation and improvements to the process because it's a continuous improvement concept. We continually want to make improvements to what we do, even when there are tabletop exercises and other ways of practicing the events. All those things are designed to identify flaws in the ways that things might be handled and to correct those so that when a real event happens, we can do the best job possible. So this methodology that we are applying, it can deal with many types of hazards, from flooding, landslides, wildfire, extreme weather risk, earthquakes, tsunamis, drought, and any other type of hazard that can happen. This approach can actually also apply to things like chemical disasters and other things. Today's focused on forecasting. And with that, Chad, you're up.
Thank you, James. Yeah, so building off of the framework and focusing in on the monitoring and forecasting component, my section here is going to talk mostly about developing a flood forecasting and what capabilities are available. One of the first things we do need to define is what is monitoring versus forecasting. And so monitoring we define as what is happening right now, the current situation. An example of this, apart from the tools that we have, but I did hear a story about an emergency responder that would nail in a piece of rebar in the flood fringe, and that would tell him, and he would mark it as the flood would rise and recede. And so that's an example of a low-tech monitoring solution. But it tells you what is going on right now. Is the flood receding? Is it what stage of the storm are you in? And you can make your decisions based off of that. The forecasting is telling you what is going to happen in the future. And there are various rainfall forecasting models. There's the HER, the NDFD, NCEP. Those are all NOAA, National Weather Service models. They give you a forecast at a specific lead time, whether that be 7 days or 72 hours for the NDFD. The NCEP and MDFD are updated every 6 hours, so it's a continual updating process. The HER is updated every hour and gives you an 18-hour lead time. And the preview is an actual product that we develop, and it's more of a nowcast, and it takes, instead of a forecast like the others, it'll take the current radar and rainfall and project it or translate it out an hour. So that gives you real-time data based off of the storm's motion and intensity on what it's going to probably do in the next hour. So various models have various lead times, and they're updated at different intervals, but that can be integrated in order to help you make decisions in those time frames. Obviously, the models with the longest lead time have the most uncertainty, but as the storm gets closer and closer, you could adjust your planning accordingly. Some of the current tools, we mentioned the forecast, but there's also remote sensing or satellite data that's used. Sometimes I've heard of the FEMA flood maps being used to identify different areas of risk. That's not really a forecasting tool, but if you don't have anything, that's been used to identify where the storm event might impact. There's a lot of local knowledge. The senior staff that knows all about the different rain gauges, and when a certain rain gauge hits a certain depth, then you have an idea of certain bridges or certain infrastructure that might be at risk for flooding. Definite drawback there is with senior staff retiring, where does that knowledge go? But overall, it's all about lead time. So an increase in lead time leads to a decrease in risk. That lead time, the more time that you have, you could prepare better. You could allocate resources where they need to be. You have more time to warn the public. So the forecasting component adds to that lead time. So at different stages, you can have different forecasts, I guess, certainty levels, and plan accordingly. So before the storm happens, certain things can happen at certain times based off of these forecasts. So bringing in is, so we have those different forecasts at the different lead times. How do we translate that into flood inundation or flood mapping? There are different variables converting a rainfall forecast to a flood forecast. Part of it is the rainfall component, which is the driving factor. So the meteorological variables, how quickly is the storm moving? How intense is the storm? Are there any training echoes or back-to-back storm effects that you need to worry about? And then there's the surface component. So surface water runoff is dependent on soil type and soil saturation. How much water is going to infiltrate as opposed to run off is a key factor. The vegetation and land cover for the area. The terrain slopes. Do you have steep channelized slopes? Are you on alluvial floodplain? Are you down by a real flat area? All those are components to the surface water runoff. And then there's current runoff conditions. This is a catch-all for any kind of man-made infrastructure or other kind of conditions. Maybe there's different dam releases and things that you have to be concerned about. All those need to be taken into account, as that could affect what the actual surface water runoff is for a particular. You could have a storm event, two relatively minor storm events that are back to back, and the first storm event can saturate your watershed, and the second storm event can be a much larger flood event than it would have had been otherwise, depending on the different characteristics. So building these flood forecasting models, at AEM we have our own internal model called VFlow. VFlow is a computational hydraulic model that takes rainfall as the input and outputs flood depths and velocities. It is geared specifically for flood warning applications. So it's designed to run very quickly, but can be used in a variety of different applications, including the real-time flood prediction forecasting. When the new flood forecast comes out, you could run that through the VFlow model and see what that forecast might translate to as far as flood inundation footprints and flood depths through your area. That again supports operations and emergency management. That increased in lead time, you could run those forecasts through the model, and then that output then can be used for decision-making purposes, where to allocate resources, where to warn the public. Obviously, the decision to do so has to be also weighted against the uncertainty of the forecast as well. But the closer the storm gets, the more certain the forecast gets, and the decisions can be adjusted accordingly. Stormwater management can be assisted. If you have debris, preventative maintenance, checking on areas of detention, making sure that your stormwater system's functioning properly. Even the utility side, oftentimes treatment plants or pump stations are located in near rivers and streams, and warnings can be developed and actions can be taken to help prevent the loss of life or infrastructure. And even some of our clients, they use reservoir operations, or they do some preemptive drawdowns in some larger detention areas to account for the storm as it's coming. With real-time and predictive hydrologic modeling, we do want to compare our model results to observed values to see the performance of our model. This allows us to increase the confidence in the model results. As you can see here in these plots, we have a red observed stage line, and there's a vertical line that shows the current time step. And then the blue line is our modeled results that extends out into the future. So as our forecast model results get observed values to compare with, you can compare that model results with the observed values and see how the model is performing. This gauges your confidence in the model, also the confidence in your decision-making process. Oftentimes, model results are thrown out just because you're not sure if it's how accurate those results are. So this is a way that you could compare your predictive to the real-time scenarios. Modeling is a tool. It is not the end-all be-all, but can be a very useful tool in flood response. Also in post-event, you could look at the model observed values and see how did the model perform. There's statistics and different metrics that you could use. No model is valid forever. As watersheds change over time, recalibration may be necessary, but these metrics can be used to determine that over time. So inundation or flood inundation forecasting increases your lead time. Again, that increase in lead time leads to a decrease in risk. You're able to have more time to allocate resources and implement your emergency plans. It gives you more knowledge where data might be limited. If you have a watershed that does not have a gauge, it gives you some information on what might occur there. There's the comparison to what is observed, so you can look at how does the forecast compare to what actually happened, and it's a system that can be continually improved. All right, with that, I will turn the time back over to Mike.
All right, Chad, thank you very much. That was some great information that you shared, as well as James. And it looks like it sparked some really great questions from the audience. We'll go ahead and dive into some of those questions now. And first up, we've got Chad. You had mentioned one of the key issues with forecasting is providing sufficient lead time. About how much additional lead time should someone be looking to achieve with flood forecast? Are we talking a couple of minutes, a few hours, a few days? How far into the future do they need to be looking?
The more lead time, the better, right? That gives you more time to implement your plan. When we talked about those forecasting models, the NCEP goes out to 7 days in advance, all the way down to the preview, which is 1 hour in advance. Obviously, with the further out you go with your forecast, the more uncertain you are. But even knowing that the storm might be coming, and then that you could take certain steps at that 7-day mark to prepare, and then as the storm comes and as you gain certainty, as the storm gets closer and closer, you could take additional steps. So it's all part of the planning process. There might be certain resources or certain things you could do at the 7-day mark, but then as the storm comes, you can either see has the storm adjusted or changed as it gets closer and closer, and then adjust your plan as it gets. So the short answer is the more lead time, the better.
That's great. And so as flood conditions get up on you and you rerun these forecasts, how long does it take the flood forecast model to run?
So the model forecast, it's in the 5 to 10 minute range, so it runs very quickly. And so with the preview, we're getting updates. That's a 1 hour forecast that's updated every 5 minutes. And so the model will run within that time frame. And then everything else, they're updated either on the hour or every 6 hours. And so the model is not the limiting factor. It's just when can we get a new update from the forecast models?
That makes sense. That makes sense. And then here's a question about, so obviously conditions in a community or an environment, they're dynamic. More development's always being done, new roads coming in, new impermeable surfaces being built. And so this user notes that obviously those models need to be updated every so often. What's the best practice on time frame for updating those?
Yeah, that's a good question. What we do is we look at it on a storm by storm basis. Usually we'll look at the medium to large storm events. Some of the smaller storm events, the models are calibrated to the large flood events. But yeah, it's looking at how does your model compare to observed? And then if you see that deviation, then you could start looking into why that deviation might be occurring. We look at it on a year by year basis and look at how the observed data compares to our modeled results. And if we're seeing good metrics, then we make recommendations to our clients. But ultimately, you will have to recalibrate. Things change. One model is not static. Things are always changing, whether it be development or just different assumptions that the model has.
Great, thank you, Chad. Here's an interesting question. How does the AEM flood forecasting approach compare to the NOAA National Water Model approach?
So the National Water Model, it's a nationwide model, so it's much more general. With our approach, we look at the local. However, there's no problem with having more information where you look at the national water results as well as the AEM results. But the scale is the main difference, where the National Water Model is running for the entire nation and can give you some general ideas. With our approach, we're much more focused on specific watersheds, so more detailed analysis is done.
That's great, Chad, thank you. Here's another one. In addition to the weather models that you get incorporated into the forecast, is there any readily available radar data just to try and improve the early warnings with maybe continuous rainfall?
We have a gridded radar rainfall product, GAR, and so that's used in the preview product that I mentioned before, but that's a real-time data set, not necessarily a forecasted data set. The preview takes that GAR and projects it out forward an hour.
Real-time rainfall estimates derived from weather radar are predicted up to 6 hours ahead with a resolution of 1 mile square. This is from one of our audience members. What progress is being made to link these rainfall forecasts with hydrology and flood forecast models?
I'll take that one. Chad was talking before about the GAR product that we use right now. So we use radar, and right now the data that we're providing is a grid of 1 kilometer resolution, and we provide the data in 5-minute time steps. So the ability to have that spatial resolution of the rainfall improves the model quite a bit, because we don't just treat all the rainfall as falling at the same time in a watershed, but it might be falling faster in the upper part of the watershed and lower levels in the lower part. And that can be taken into account with the models that we run. And so it allows the model itself to run better because of that. And the 1 kilometer resolution, that's our current sort of standard resolution. There are some radars that even have higher resolution, and our software is capable of using that. But we have, at this point, we've standardized because we can provide 1 kilometer resolution rainfall data continuously over the air. For our customers that have radar systems, we can provide that continuously across the United States, Canada, Australia, places like that, where they have radar networks where we can pull the data and do that processing. We also have gauge adjusted radar rainfall in the design of some of the systems we've been doing for some other countries too, where we're helping them build their own radar networks and then bring the data together so they have a continuous gridded rainfall data product that they can use for their own forecasting and in other countries.
Here's an interesting question. It looks like some of the examples that we were drawing on in this presentation, or maybe some larger river systems, overland flood areas. This user says that their particular issue is they're in a smaller mountainous watershed where they're looking at areas that can be as small as 20 square miles to a square kilometer to 52 square kilometers, or a third of a mile up to 20 square miles. And those areas are prone to debris flows and debris floods. Does our forecasting take any of that into account, or do we have ways of forecasting for these?
So we just completed a project where we did the design of a system for also monitoring debris flows. And in general, the way we have to handle debris flows, because they're hard to predict with a model, is that we use the model to predict the flooding and the saturation of the soil and things that could trigger debris flows. But we basically are providing information as to how much risk there is of a debris flow happening up until it does happen. And then when it does happen, we try to put sensors to do the monitoring, like Chad was discussing, how monitoring tells you what's happening. There are some specialized monitoring stations that can detect debris flowing down areas, and so they're designed differently than a standard stream level gauge that just gives you the water level. They're designed to detect mass movement of debris through an area, and then it triggers the station to report. So those are the ways those things are handled. They're very hard to predict with modeling, though. What we really are doing is predicting the risk of it happening more than being able to tell you exactly when a debris flow is going to happen.
Thank you, James. That's really helpful. Here's another one about potential use cases. Does the system account for backwater effects, overtopping culverts, or man-made obstructions in urban channels?
So I could take that. I would say, yeah, it definitely does backwater effects. There are options for culverts and different infrastructure. What I will say though is that it does not know if your culvert is clogged during the storm event. You have to design the model beforehand, and so it wouldn't pick up if the debris flow clogs up a culvert, but definitely does backwater and culverts and different typical stormwater infrastructure.
Thank you, Chad. Very helpful. How does the system resolve discrepancies between data sources, whether that's a Davis station versus in your own network, or a satellite-based precipitation data versus a local gauge measurement?
The software that we use, first of all the data is real-time quality control. So we have, in the software itself, we run a whole bunch of quality control algorithms on the data as it's being collected. And so every data point is given a quality control flag, and the ones that have A's or variations of A's in them are the highest quality data and the data that should be used. And then any of the other data points that have other flags on them, they might be flagged because they're duplicate data, or they might be flagged because they had too large of a jump between data points, or the data itself might not be consistent with other sensors that are nearby. Maybe it's a temperature reading and it's off by 10 degrees of other sensors that are nearby. There's all these types of quality controls that go on the data that comes in. And so at that point, you at least have data that's had some quality control on it, though it's this real-time stuff that has to be automated. And then, so for all the stuff we're talking about here, that's the type of data we're using, which is real-time data, because there isn't time for somebody to go in and manually make decisions about the quality of data when you're running these models and you need the data that was collected 5 minutes ago. In any case, there is quality control checks on everything. And when data disagrees, one of the things we do long-term is we look at events after the fact, and we look at how well the sensors performed during the event that happened. Let's just say there was a flood event that happened 2 weeks ago, and we go back and reanalyze that data. And if any of the stations were not producing data consistent with the event that actually happened, then those gauges get turned off as being used by the system, so that the next storm event, those sites don't get used unless somebody goes and does maintenance or comes back and says, we went to the station, we found out that there was a bird had built a nest in the rain gauge and it was messing up the rain readings, and we've cleaned it and now it's okay, or whatever, then we might put it back into use again. But we also do that, which is after the fact curating of the stations, whether or not they produce quality data, and we don't use them in the next events until somebody has done something specifically to repair that station and say it should be producing quality data again.
Great. Thank you, James. Can the system simulate multiple flooding scenarios based on different precipitation intensities or storm tracks?
Yeah, you could do different scenario-based applications. You could use historical rainfall and amplify it. So if a storm happened and you wanted to see how much, if it was twice as large or if it came from a different direction, how that might affect things, as well as the forecast. If the forecast's ahead of time, if it's coming and you could see it and you want to double it and see how that might affect, there's tools for that. Just running that data set through the same model.
Great. Thank you, Chad. And thanks to all of you for attending. So thanks again and have a great day.